now. As the night settles over every familiar sound of Earth, allow your mind to drift just a little, like you're resting inside a soft, quiet spacecraft where everything feels as light as a passing breeze. Imagine that spacecraft gliding smoothly through a velvet dark sky, silently circling the sun. Outside the window in your imagination, thin ribbons of light shimmer from the planets following their ancient orbits. There's no rush, no need to hold on tightly to anything. Just let your thoughts loosen, growing weightless like stardust, floating, drifting, dissolving into the vast, open space around you. In this calm, there is one question humanity has whispered to the cosmos for centuries. A question both tiny and immense. One that can make anyone, whether they've studied the night sky or only glanced at it once, pause for a heartbeat. Has Mars ever hosted life? That red world, seemingly nothing more than dust and cold stone, carries faint, lingering traces of flowing water, of lakes, of ancient seas. If those places truly existed for millions of years, could life, perhaps no more than a single lonely cell, have ever sparked beneath that crimson soil? And the moment that question takes shape, another unfolds right behind it, opening wide like the entrance to an endless hallway. If Mars once had life, could there be other worlds in the solar system holding the same kind of secrets? When we think of icy moons, of oceans hidden beneath tens of miles of frozen crust, or atmospheres filled with drifting organic chemicals, it becomes hard not to wonder. Somewhere out there, might life have found its own way, its own rhythm, its own breath, in an environment utterly different from anything we know? Tonight, in this quiet moment before sleep, your journey will gently guide you through those worlds. It begins with Mars, the dry, familiar neighbor of Earth. The red planet captivates not only because of its color or its sweeping dust storms, but because of the geological clues science simply cannot ignore. Valleys that look carved by ancient rivers, sediments worn smooth by long-vanished water, minerals that only form when liquid water lingers for ages. Each clue is like a puzzle piece, small, delicate, but essential, waiting for humanity to assemble them into an answer about life. Then the journey carries you farther, past Mars's orbit, across the stillness of space toward the great gas giants. Amid their swirling storms, the moons of Jupiter and Saturn tell a very different story. Some hide dark, endless oceans so vast that every ocean on Earth combined would be just a thin mist compared to them. Some release plumes of water, rising like a planet's breath, carrying salt, organic molecules, and subtle hints of the chemical reactions that might sustain life. Others, like Titan, tell their stories without liquid water at all. Instead, its lakes of methane and ethane suggest a bolder possibility, that life might not need water to exist. In its thick, amber atmosphere, organic chemistry has been unfolding for billions of years, weaving molecular chains that, on Earth, usually accompany biological processes. We cannot say anything for certain yet, but Titan continues to draw our quiet, persistent curiosity. And finally, the journey gathers all of this together, light as a blink, to pose a simple question that has followed humanity for generations. If our solar system offers so many environments, so many ways to create and protect water, so many sources of energy, is life truly as rare as we once believed? Or have we simply not traveled close enough to notice its faintest signs? Throughout this journey, you don't need to memorize a single fact. The scientific details, the planets, the hidden oceans, the layers of ancient sediment, They can drift by like reflections on a dark lake at night. They don't need sharp focus. They only need to settle softly in your mind, so your imagination can keep traveling even after your eyes begin to close. This is a bedtime story, a gentle doorway into worlds we've never set foot on, yet never stop dreaming about. A story where science and wonder don't oppose each other, but merge like two quiet streams meeting in the stillness of space. All you need to do is relax and step into that journey, letting humanity's oldest questions soften like the wind brushing across Mars's red dunes. And as you listen, let each word drift past you like falling stardust, because tonight, together, we begin searching for the answers to the secrets the solar system has kept hidden for billions of years. After letting your mind drift gently through the red, blue, white, and amber worlds of the solar system, perhaps it's time to return to a more fundamental question. A question so seemingly simple that everyone thinks they know the answer, yet it holds the key to understanding why we cannot judge life beyond Earth solely through our own experience. Because to truly search for life elsewhere, we must first understand, what does life, at least Earth-like life, need in order to exist? Humans are the easiest place to begin. This body, though it appears sturdy and adaptable to many environments, is actually dependent on a list of conditions far more delicate than we imagine. We need oxygen to maintain the biochemical rhythms inside every cell. We need liquid water to regulate, to transport, to hold heat. We need moderate temperatures, not so hot that proteins collapse, not so cold that chemical reactions slow to a paralyzing crawl. We need stable pressure so fluids don't boil in our veins, so breathing unfolds the way it should. With just one of these factors pushed too far, the human body becomes as fragile as a thin layer of ice on a winter lake. If the environment heats up like a room filled with furnaces, where the air reaches temperatures that cause any drop of water to evaporate the moment it appears, the human body survives only minutes. On the other hand, if it grows colder than the harshest Antarctic days, the fluids in our cells begin to freeze into sharp crystals, tearing apart the biological structures needed for life. Too little pressure and the moisture in our lungs boils away. Too much pressure and soft tissues feel crushed between solid plates. Humans are a rather fragile form of life, perfectly adapted to Earth's sheltering conditions, but unable to step freely into the cosmos without layers of protective technology. But here is the fascinating part. Even on Earth, a place we believe we know so well, countless organisms thrive in conditions humans would call unbearable. Every time we look at them, science has to pause, step back, and expand its definition of what it means to survive. In hot springs near 100 degrees, where water bubbles like a boiling pot, certain bacteria live comfortably. They don't merely exist, they flourish. To them, extreme heat isn't a threat. It's simply the way life feels. Under massive sheets of polar ice, where sunlight can't penetrate and temperatures fall so low that most biological reactions nearly freeze, microorganisms persist for hundreds, even thousands of years. They consume energy slowly, repair themselves slowly, and maintain a rhythm of life that, compared with humans, is almost like sleeping through an endless dream. Some organisms survive in salt levels so high that ordinary cells would shrivel instantly. Others thrive in acids strong enough to dissolve metal. Some live without oxygen at all, using different molecules to power their bodies. Each extreme environment expands the meaning of survival far beyond what humans once imagined. If you look at a map of Earth's ecosystems, you can see that life has rooted itself in places the human imagination once believed completely empty. Each time we discover another extreme survivor, the planet whispers that life doesn't chase comfort. Life chases opportunity. Whether it's a faint trickle of energy at the ocean floor, a hint of warmth beneath frozen soil, or a thin film of water trapped inside mineral cracks, life finds a way to use it, transform it, and endure. From this, a gentle yet daring hypothesis emerges. If life on Earth can adapt so completely, then in the solar system, where similar or even harsher conditions exist, why couldn't tiny, resilient organisms survive in their own quiet ways? On Mars, where temperatures often sink below freezing, where the atmosphere is thin as tissue paper, and where liquid water struggles to remain on the surface, minerals still point to a past that was far more humid. In cracks between rocks, beneath a thin layer of soil, there may be pockets just a little warmer, a little moister, enough to keep a simple form of life running at an incredibly slow pace. Earth's own microbes have already shown us. With a hint of moisture, a trace of heat, and the faintest energy source, life can persist for millions of years. On Europa or Enceladus, where miles of ice conceal dark oceans with no sunlight and no solid surface for photosynthesis, life could draw energy from tidal forces and hydrothermal activity. What happens at Earth's deep-sea vents, where sunlight never reaches yet entire ecosystems flourish, reminds us that life can follow many different paths. When imagining these worlds, it feels as though the universe is softly reminding us that human conditions are just one special case, not a universal rule. If life can be as flexible as the examples we see on our own planet, then beneath Europa's thick ice, in Enceladus's hidden sea, or within the once warm soils of ancient Mars, there might be small, resilient, silent forms of life waiting for us to discover. And with that thought, a gentle conclusion appears, like a thin layer of mist drifting across still water. What humans call harsh may simply be an opinion shaped by a creature accustomed to Earth's familiar air. The universe is far broader than that. It may hold forms of life for whom the most unusual, most extreme conditions are not obstacles at all, but their natural home. After reflecting on the astonishing diversity of life on Earth, and realizing that living organisms can endure in places we once thought completely impossible, a natural question rises next, like a gentle ripple spreading across a still lake. If extraterrestrial life can exist in its own unique ways, then how does science search for it? In a universe so vast, we rarely see creatures moving openly or calling out to us. Instead, what science looks for are usually the invisible clues, the indirect hints, the faint traces left behind long after time has erased the life that might have once been there. That is why the concept of biosignatures came to be. A biosignature doesn't need to be the intact shape of an organism. It can be the faintest sign of a biological process. On the surface of a distant planet, where robots must navigate through cold winds on their own, these signs might appear as tiny rock structures, simple or complex organic molecules, or unusual changes in the composition of the atmosphere. One of the oldest signs science seeks is layered sedimentary structures or patterns suggesting ancient microbes once lived in water. On Earth, these structures exist in ancient sedimentary rocks, formed where communities of bacteria created distinctive layers. When robots on other worlds drill into rock and find similar patterns, we cannot declare it proof of life, yet it becomes an invitation to look closer. Another kind of biosignature comes from chemistry, organic molecules. Even though life elsewhere might not use carbon the way Earth's life does, carbon is still the backbone of many biological processes here. So when a rover discovers organic molecules in Martian soil, or when a spacecraft detects organic compounds in the plumes bursting from Enceladus. It feels like hearing a distant echo from the past, as though something once happened in the darkness of deep time. Planetary atmospheres also carry valuable information. Some gases, like methane, can be created by geology, but they can also be produced by living things. When methane on a planet rises and falls with the seasons, increasing and decreasing in a repeating rhythm, science cannot help but pause and wonder, is this the work of life, or a natural process we have yet to understand? That question still hangs over Mars, where methane occasionally appears in sudden bursts, like a whisper from its thin, reddish sky. To search for these signs, science relies on a suite of sophisticated instruments, extensions of our senses. In orbit around planets, spacecraft observe surfaces through electronic eyes capable of seeing wavelengths invisible to humans. They capture high-resolution images, measure mineral compositions, analyze atmospheres from afar, and track changes over time. Each picture sent home is like a new page in a planet's unfolding story. When the surface must be touched directly, landers descend and settle softly onto carefully chosen locations. There, instruments analyze soil and rock on the spot, measuring moisture, crystal structure, and chemical makeup. They are tiny laboratories working alone in alien environments, separating each grain of dust, reading each layer of sediment, searching for anything unusual. And most important of all for many missions are the rovers, robotic geologists with the ability to move. They climb slopes, cross rocky plains, wander into dried riverbeds, and impact craters. Every meter they travel is planned to maximize the chance of finding biosignatures. When a rover drills into a rock and sends back the results, it isn't just cold data. It's a sentence in the story the planet is slowly revealing. The role of geology in the search for life is so essential that many scientists compare each landscape, each layer of rock, to a page in a planetary diary. A crater filled with layered sediments shows that water once pooled and settled there. A long, winding valley hints that a river once carved its way through. A rocky surface containing minerals that only form in wet environments suggests that liquid water persisted for a long time. And while water isn't the only requirement for life, it is one of the most important ingredients for many biological reactions we understand. By reading geological stories, science learns more than whether a planet was once warm or cold, wet or dry. It identifies where mud once collected, where organic matter might have settled, where volcanic activity might have released gases into the sky. These details don't prove life existed, but they show that the environment once held conditions favorable to life. And when we look at the map of worlds where science listens for these clues, there is one place that has always stirred something especially deep in the human heart. A world where every dried streambed, every tilted layer of rock, every grain of red dust seems to guard an ancient secret. A place not too far away, not too hard to reach, and filled with so many hints that science cannot look away. A place where the question of life seems to echo louder than anywhere else. And that world is Mars. When those invisible clues begin to guide us closer to the story of life itself, there is one world that always stands at the very center of the search. A world not too distant for our eyes to reach, yet not too cold or immense for our robots to explore. After moving through the idea of biosignatures and the way science listens for the faintest whispers from distant planets, we naturally find ourselves being led toward the place where every question seems to converge. And when the door finally opens, Standing quietly before us is Mars, the red planet, where every grain of dust feels like it's hiding a secret from long ago. Mars appears not as a lush world of green, but as a vast desert stretching unbroken toward the horizon. Its surface is blanketed in red sand, a deep brick-red color, as if it has been fired by billions of years of sunlight. Scattered among the dunes are fields of jagged rocks, sharp-edged stones carved down by winds that have blown for countless dusty seasons. In some places, the land rises into strange formations, as though water once flowed there and then vanished abruptly, leaving behind silent imprints etched into the sand. In the Martian sky, the light carries a soft, hazy shade of amber. The sun, the very same star that nourishes life on Earth, appears much smaller here, just a pale dot shimmering through the thin air. Looking up at that sky, one can't help but feel the distance, as though the light had to travel a little farther, breathe a little deeper before touching the ground. And from time to time, enormous dust storms sweep across the plains, lifting the desert into the air and wrapping the entire planet in a dim veil that can linger for days, sometimes weeks. In this world that seems so still, the environmental numbers tell a harsher story. Temperatures on Mars often dip well below freezing, and at night, they can plunge into levels of cold that challenge the imagination. The atmosphere is so thin that its pressure is less than 1% of Earth's, making liquid water almost impossible to sustain on the surface. It either evaporates or freezes nearly instantly. The air we see is mostly carbon dioxide, so thin and frigid that a human could not take even a single breath of it. And though the winds sometimes reach high speeds, they carry too little air to truly push against anything the way Earth's winds do. When imagining humans walking on Mars, it becomes easy to see how immense the challenges really are. Anyone standing on that surface would need a fully sealed protective suit, thick, pressure-regulated, able to hold warmth, oxygen, and life inside. For long-term living, people would need reinforced habitats, insulated greenhouses, and shelters capable of blocking cosmic radiation. Because the planet's thin atmosphere cannot shield us the way Earth's has for billions of years. Every step toward making life possible on this world demands technology, patience, and the determination of generations. But if we look only at the harshness of the present, we risk missing the most important truth. Today's Mars is merely the final chapter of a very long book. Beneath that cold desert, beneath the quiet red sand, lies a complicated history, a past completely different from the dry world we see now. And it is this past that drives scientists to keep digging, drilling into ancient rocks, photographing every crater and every layer of sediment. Because the geology of Mars is not just stone, it is the planet's diary, written in dust, minerals, and time. There are valleys stretching hundreds of kilometers, deep winding canyons cutting through plateaus, and wide basins shaped like the beds of vanished rivers, all hinting at an age when water once flowed freely across the land. In some places, flat plains resemble the floors of ancient lakes, where water settled and left behind fine layers of sediment. Craters reveal beautifully stacked rock layers, like pages of a book, each one holding a record of a climate long gone. Pale gray layers mark cold, dry times. Deep reddish layers formed when water interacted with rock. And certain clay minerals appear only when liquid water is present for long periods. Looking at those minerals, scientists don't just see evidence of water, they see the essential conditions life would have needed to remain stable. Water, time, and the right chemistry, all of these once existed here. And even though the planet today holds only red sand and a dusty sky, that past has never vanished. It rests quietly in every rock, every sediment deposit, every particle of dust. That is why, even though Mars is harsh for humans today, its pull has never faded. The harshness doesn't make it less captivating. In fact, the contrast between its cold present and its once wet, warmer past makes it one of the most compelling places to seek answers about life. Because if a planet once had lakes, rivers, oceans, warm climates, and minerals shaped by water, then something profound must have happened. And the deeper question lingers. During that chapter of warmth and water, did life ever have the chance to begin? When one gazes at the amber sky of Mars and the endless red sands stretching outward, they don't simply see a desert. They see a place that once moved to a different rhythm, lived under a different climate, carried a story that the winds have weathered but never erased completely. And because of that, every rock on Mars could be a memory, every canyon a quiet note, every dried basin a reminder that life might once have been very close. And when all these pieces of evidence are gathered together, one truth shines as gently as the small sun glowing in the red sky. Beneath its dry, frozen, dust-covered exterior, Mars is not a dead world. It is a world holding powerful hints of a once vibrant past. And this is where the planet's geology speaks the loudest, softly telling the stories that billions of years have tried to hide. When we look at Mars today, its cold deserts and its endless drifting dust storms, it can feel almost impossible to imagine that this dry, barren world once wore a completely different face. Yet the rocks, the valleys, and the silent plains whisper another story, one that scientists have patiently listened to for decades. And that story begins with something that sounds almost like an ancient legend. Billions of years ago, Mars may not have been harsh at all. In the scientific imagination, the tale of ancient Mars often opens with a gentle suggestion. Billions of years ago, Mars may not have been as dry and rigid as it is now. And from that single idea, the geological clues begin to fall into place, one after another, like puzzle pieces waiting to align. Once assembled, they reveal a picture of a world where water once flowed, where lakes shimmered, and perhaps even where deep oceans stretched toward the horizon. In the earliest satellite photos sent back from Martian orbit, scientists saw long valleys winding softly across high plateaus. These valleys didn't look like cracks created by meteor impacts, but carried the familiar, graceful curves of ancient rivers. Some sections appeared as broad riverbeds, others narrowed like gentle streams. They wound through the landscape as though shaped by water moving steadily over long periods of time. No pattern of wind erosion could carve such shapes, leaving researchers with only one conclusion. Water had been there, but the valleys were just the beginning. Across the Martian surface, strange fan-shaped plains appeared, broad triangular structures spreading outward from a single point. On Earth, such formations arise only when rivers carry mud, sand, and minerals downhill, slowing as they reach a low, open space and gently fanning out where they meet a lake or sea. Seeing the same shapes on Mars, scientists could almost sense the memory of streams emptying into ancient basins. There are also places on Mars that are eerily flat, so smooth and expansive that even the strongest winds couldn't have shaped them. These plains stretch for hundreds of kilometers, their fine sediments layered again and again. For many scientists, these regions represent the remnants of ancient seas. Some even have what appear to be shorelines, as if Martian oceans once rose and fell in slow, rhythmic cycles. The fine sediments resemble the kind of soft mud that settles at the bottom of still water. Each layer a season, a year, a century of the planet's past. But it isn't only the landscapes that speak of water. The minerals on Mars act as quiet witnesses too. In soil and rock samples collected by rovers, scientists discovered clay, minerals that form only when water and rock interact over long periods. Where there is clay, water must have lingered, patiently breaking down the original stone and reshaping it into new layers of material. Such transformation can't happen in a dry or frozen world. It needs a wet, sustained environment. And beyond clay, Mars holds salt as well. Salt appears only when water evaporates, leaving behind crystallized minerals. Finding ancient salts on Mars offered strong evidence that water once pooled, evaporated, returned, and repeated those cycles, much like lakes in Earth's semi-desert regions. Even certain sulfates point to the presence of strong, flowing water capable of oxidizing its surroundings. These minerals serve as testimony written in stone. Each clay layer, each grain of salt, is a small fragment of information about a long period of moisture, perhaps not for just years or centuries, but for millions of years, enough time for rivers to form, lakes to spread wide, and oceans to grow shallow and bright. As these clues knit together, a soft yet unmistakably clear image emerges. Ancient Mars was warmer, wetter, and sustained a water cycle similar to early Earth's. Its skies may once have held drifting white clouds, with occasional rain falling gently into its valleys. Rivers might have stretched across the land, merging into great lakes. Vast, shallow seas may have reflected the dim afternoon sunlight in shades of pink and gold, scenes no one alive today will ever witness. This hypothesis becomes ever more convincing, not only because the shapes of the land resemble water's craftsmanship, but also because the telltale minerals appear in abundance. In many regions, there's even a clear transition between rock layers formed in wet conditions and those shaped later by dryness, like chapters in a book describing the planet's shifting climate. And when that picture is finally complete, the great question of life rises, not loudly, but softly, with weight and wonder. If liquid water existed for so long, and if the early climate was warm and stable enough for clay and salts to form over extended periods, then microbial life, the simplest, most resilient kind, might once have emerged on Mars. No one claims that life grew complex. Perhaps it existed only as tiny single-celled organisms drifting through water, clinging to stones, living in shallow lakes, or beneath soft layers of mud. But even the thought that such small beings could have lived on another world in our solar system is enough to deepen the meaning of every effort we make to explore. Today, when people look at Mars and see a cold, red planet, they no longer see a dead world. They see a world that once lived, once warm, once wet, once shaped by flowing water and gentle winds. A world that once sparkled with the reflections of ancient seas, once felt soft rain, once had nights filled with clouds drifting across its sky. A world that shifted through vast transformations, from wet to dry, from warm to cold. And it is this watery past that keeps science searching with patience and devotion. Because if life ever began there, even once, even in the smallest microbial form, then the story of our place in the universe would be forever changed. As the traces of ancient water on Mars become clearer, through its dry valleys, its fan-shaped plains, and its layers of clay minerals, the story of the red planet leads us into another chapter, deeper and grander than before. If water once flowed through those valleys, if ancient seas once glimmered in the distant sunlight, then what changed this world so dramatically that it is now nothing more than a cold desert? And to understand that transformation, there is nothing more important than looking into the planet's very structure. Its mountains, its canyons, its stacked layers of rock like pages in a stone-bound book written by time. Mars, though silent, carries landscapes so immense that anyone standing before them would feel impossibly small. And towering above all of them is Olympus Mons, the largest volcano in the entire solar system. If Everest is one of Earth's great peaks, then Olympus Mons is a world unto itself. It rises 3 times higher than Everest, and its base is so wide that if you stood at its edge, your eyes could barely detect the slope curving up toward the summit. Imagining yourself standing beneath Olympus Mons is like picturing a vast red plain stretching endlessly outward, beneath a thin sky where sunlight softens and the wind moves without weight. The ground feels like a blanket of fine dust, and ahead rises the massive wall of nature, built from countless ancient eruptions. Olympus Mons is not merely a mountain, it is evidence of Mars's once fierce geological past. Earth's tectonic plates shift over time, dispersing volcanic material across the planet. But Mars lacks such motion, and so a single hotspot erupted for millions of years, building a mountain unlike anything seen elsewhere. This reveals that long ago, the planet was far more active, with a hot core and powerful volcanic processes, essential ingredients for renewing environments and creating atmospheres. But if Olympus Mons represents upward force and rising fire, then on the opposite end of the story lies a structure shaped by collapse. Valles Marineris, a canyon stretching across the planet like a scar. Valles Marineris spans more than 4,000 kilometers, wide for hundreds more, and plunges deeper than any canyon on Earth. Seen from orbit, it looks as though a giant blade sliced through the Martian crust, leaving a wound that has never healed. The canyon's towering rock walls expose layers upon layers of sediment, stacked like ancient pages. Each layer marks a time period, a climate, a planetary cycle. Some layers formed during dry eras, others when water once flowed. Some eroded by wind, others buried and revealed again across billions of years. To geologists, these are not just rock strata. They are chapters of the planet's history written in stone. Even the impact craters hold countless memories. When a large meteor strikes the surface, the force lifts deep rock layers upward, exposing sediments that normally remain hidden in darkness. Some craters reveal ancient clay, the kind that forms only when water was once present. Others expose sulfate minerals, hinting at periods when the environment grew more acidic. Still others reveal basalt from old lava flows, marking times when volcanic eruptions reshaped entire regions. And then there are the remnants of ancient lake basins, smooth, quiet depressions edged by rings of layered sediment, like faint ripples drawn by time itself. In these places, the layers record water rising and falling. The lowest layers bear traces of wet mud. Those above show minerals shaped by wind. The next layers, again, show water's return. These cycles reveal that Mars once underwent many shifts, wet to dry, warm to cold, building a long, intricate record of climate change. When the rovers drill into these layers, they aren't just collecting samples. They are reaching into the deep past of a world. Each core of rock lifted from the ground is like a question. Could microbial activity have once existed here? Could organic molecules be hidden within sediments laid down billions of years ago? Could certain textures resemble patterns left by ancient bacteria? Every analyzed rock is not just material. It is a piece of memory, a quiet clue about whether life may once have touched this planet. Geology is more than studying stone. It is decoding a world story. And on Mars, that story has never been simple. From colossal volcanoes like Olympus Mons to vast canyons like Valles Marineris, from ancient lake beds to delicate sediment layers, everything comes together to create a multi-layered portrait of a world that was once dynamic and ever-changing. Seen as a whole, Mars is not only beautiful in a strange way, it is beautiful in a profound way because of what it remembers. Its mountains stand like towering memories. Its canyons open like scars that never fully healed. Its sediments read like quiet lines describing seasons of water, seasons of dryness, and the long evolution of climate across millions of years. And thanks to geology, we learn that the question of life on Mars cannot be answered by a simple glance at its surface. It must be answered by turning every page of its stone-bound history, by reading every mineral, by listening to every clue the planet has left behind. Mars is not just a place to look at. It is an ancient book, and each person who studies it is a patient reader, searching carefully to discover whether somewhere within those pages, life was ever written. After following the towering mountains and the deep canyon-like scars carved into Mars, the story leads us naturally to an obvious truth. While the planet's geology tells us so much, to truly read that stone-bound book, we need eyes that can get close, hands that can touch the rocks, and minds that can analyze each sediment sample right where it lies. And because humans cannot yet stand on Mars, for decades we have sent steel explorers, patient robots carrying the mission of uncovering the planet's history and searching for signs of life. That journey began with the Viking missions, like two early visitors arriving on the silent terrain of the Red Planet. Viking 1 and Viking 2 were more than landers. They were pioneers opening a new era. When they touched down on Mars, their mission was to perform simple yet daring experiments, to see whether Martian soil showed any biological reactions. The results didn't provide a clear answer, but they created the foundation for understanding just how complex the search for life on another world would be. Viking was like the first greeting, an initial, curious glance into an unfamiliar world. Years later, Spirit and Opportunity entered the story like two enthusiastic siblings. Launched together and sent to different locations, they shared the same purpose: wander across the desert, study rocks, search for traces of water. And those two steel explorers did more than anyone had ever imagined. Spirit crawled across black volcanic stones in an ancient lava field and accidentally uncovered evidence of rocks altered by water. Opportunity traveled tens of kilometers across Red Desert, far beyond its original design, discovering tiny hematite spheres, clear signs that water had once flowed. These discoveries were like opening the first pages of Mars's stone-bound book, where the writing was still bold and easy to read. Then came Curiosity, not just a robot, but a full-fledged geologist on wheels. Curiosity was sent to Gale Crater, a site with a central mountain whose layered sediments rise like a timeline molded in stone. There, Curiosity drilled into ancient rock and analyzed long-dried mud once sitting at the bottom of an ancient lake. The samples revealed that Gale Crater once had the right chemical conditions for microbes to survive: neutral pH, useful minerals, and stable liquid water. As Curiosity climbed the sediment layers, it was as if it were reading chapter after chapter of Mars's climate history, each layer a memory captured across billions of years. And then came Perseverance, the newest and most advanced explorer, touching down in Jezero crater, once a river delta flowing into an ancient lake. At Jezero, the presence of past water is so unmistakable that scientists are almost certain. If Mars ever hosted microbial life, this would be the place to find its traces. Perseverance not only observes, but collects precious rock samples, sealing them inside small steel tubes to one day be returned to Earth. Those samples might hold the decisive clues to answer the question humanity has carried for decades. Did Mars once harbor life? Each of these rovers, though different in size and design, carries sophisticated instruments that act as the senses of science on a distant world. High-resolution cameras map the terrain, drills reach into ancient rock, lasers fire at stone to analyze its chemistry, and tiny onboard laboratories search for organic molecules. When a rover pauses and lowers its drill into a rock, it feels like geology itself is being interviewed. The questions aren't spoken aloud, but asked through light, heat, analysis, and data. Was this once lakebed mud? Does this mineral contain organic carbon? Does this structure resemble traces left behind by ancient microbes? And in many cases, the answer is yes. Not proof of life, but strong hints pointing toward the possibility. These steel explorers not only work tirelessly, but they also carry something deeply human within their missions. Spirit, after being trapped many times, finally fell silent, unable to send another signal. Opportunity lasted far longer than anyone dreamed, until a planet-wide dust storm covered the sky, plunging it into darkness and leaving no sunlight to recharge its batteries. When Opportunity's last signal faded into silence, the team on Earth sent a farewell message, a small thank you for a long, determined journey. Moments like that remind us that even though they are machines, each rover represents humanity's longing to explore. Today, when we see the small tracks of rover wheels pressed into the Martian dust, we recognize that through those metal footsteps, the planet has revealed so many of its secrets. No instrument is more powerful than the evidence they've brought us. That water once flowed, that environments once existed that could have supported simple life, and that within those stone samples lie faint but promising hints of ancient chemical activity. And thanks to these steel explorers, the story of life on Mars is no longer a wild guess. It has become something testable, something researchable, and one day, something that may finally be answered. After tracing the colossal mountains and the deep canyon-like scars across the Martian surface, the story naturally leads us to something obvious. Though Mars's geology tells us so much, to truly read that stone-bound book, we need eyes that can get close to the ground, hands that can touch the rocks, and minds capable of analyzing each sediment sample right where it lies. And because humans cannot yet stand on Mars, we have spent decades sending steel explorers, patient robots carrying the mission of studying the planet's history and searching for signs of life. That journey began with the Viking missions, the first guests to ever set foot on the lonely terrain of the Red Planet. Viking 1 and Viking 2 were more than landers. They were explorers opening a new chapter. When they touched down on Mars, their task was to perform simple but daring experiments, to see whether Martian soil showed any biological reactions. Those experiments did not yield a definitive answer, but they laid the very first foundation, revealing that the search for life on another planet would be anything but simple. Viking was like the first greeting, an early, wide-eyed glance into an unfamiliar world. Years later, Spirit and Opportunity entered the story like two enthusiastic siblings. Launched together, they landed at different sites but shared the same purpose: wander across the desert, observe rocks, and search for signs of ancient water. And those steel explorers achieved more than anyone ever imagined. Spirit crawled over dark stones in an ancient volcanic region and accidentally uncovered evidence of rocks once altered by water. Opportunity traveled tens of kilometers across the red sands, far beyond its expected lifespan, and discovered tiny hematite spheres, clear indicators that liquid water once flowed. These discoveries felt like turning the very first pages of Mars's stone-written book, where the letters were still bold and unmistakable. Then came curiosity, not just a robot, but a sturdy geologist on wheels. Curiosity was sent to Gale Crater, a place where a mountain rises in the center of a giant basin, its layered sediments stacked over time. Here, Curiosity drilled into stone and analyzed ancient mud once settled at the bottom of an old lake. The samples it uncovered showed that Gale Crater once had the right chemistry for microbial life: neutral pH, useful minerals, and stable liquid water. As Curiosity climbed the stratified hillsides, it seemed to be reading the chapters of Mars's climate history, each layer a memory preserved across billions of years. And then Perseverance, the newest and most advanced explorer, continued the journey by landing in Jezero Crater, once a river delta spilling into an ancient lake. In Jezero, the evidence of past water is so clear that scientists are almost certain if Mars ever hosted microbial life, this would be the place where traces might remain. Perseverance not only observes, but collects precious rock samples, sealing them inside small steel tubes to one day be returned to Earth. Those samples may contain the decisive clues needed to answer the great question humanity has carried for decades. Did Mars once harbor life? Each of these rovers, different in size, purpose, and design, carries sophisticated instruments that serve as the senses of science on a distant world. They are equipped with high-resolution cameras to study the landscape, drills that reach deep into ancient rock, lasers that fire at stone to analyze its composition, and tiny onboard laboratories capable of detecting organic molecules. When a rover pauses and lowers its drill into a rock, it feels almost like interviewing geology itself. The questions are not spoken aloud. They are asked through light, heat, analysis, and data. Was this once lakebed mud? Does this mineral contain organic carbon? Does this texture resemble traces left by ancient bacteria? And in many cases, the answer is yes. Not proof of life, but strong, promising hints. These steel explorers not only work tirelessly, they also carry a touch of human emotion in every mission. Spirit, after many struggles and moments of being stuck, finally fell silent. Opportunity endured far longer than anyone expected, until a massive dust storm darkened the sky, cutting off the sunlight it needed to recharge. When Opportunity's final signal faded, the team on Earth sent a farewell message, an expression of gratitude for a long and faithful journey. Moments like that remind us that even though these machines are made of metal, each one represents humanity's longing to explore. Today, when we look at the tiny tracks left by rover wheels across the Martian sand, we realize that through these metallic footsteps, the planet has revealed many of its secrets. No instrument speaks louder than the evidence they have uncovered. That water once flowed, that environments once existed that could support simple life, and that inside those stone samples lie faint but hopeful hints of ancient chemical activity. And thanks to these steel explorers, the story of life on Mars is no longer a distant, fanciful idea. It is something that can be tested, studied, and one day answered with certainty. When people begin to imagine a future on Mars, its first outpost, its first laboratory, and the first footprints pressed into its red dust, a quiet question slips into view. Within our solar system, is there another world once considered Earth's sister, yet destined for a completely different fate? That question naturally carries us away from Mars's orbit, across the space between planets, to a world that seems familiar at first glance, but reveals itself to be more alien than almost anywhere else. That world is Venus, the planet often called Earth's fiery, temperamental sister. Venus and Earth share nearly the same size, similar mass, and were born in the same region of the solar system. At a glance, anyone might assume such a planet would surely resemble our home in some comforting way. But the truth is the opposite. Venus stands as a clear reminder that size and position alone cannot shape a habitable world. It is a story written in fire, pressure, and unforgiving chemistry. The surface of Venus burns above 400 degrees, hot enough to melt lead, hot enough to destroy most metals humans use in daily life. That extreme heat doesn't come simply from being a little closer to the sun, but from a greenhouse effect that spiraled completely out of control. Its thick atmosphere, packed with carbon dioxide and clouds of sulfuric acid, traps heat like a colossal blanket that never lifts, leaving the surface locked in perpetual furnace-like conditions. No cool days, no cold nights, just a planet-wide kiln that never rests. The pressure at Venus's surface would crush any Earth-like organism instantly. It is nearly 100 times the pressure at sea level on Earth, the equivalent of being buried beneath nearly a kilometer of water. In such an environment, all familiar biological structures collapse. Only the toughest materials humans know can withstand it. And if the heat and pressure weren't harsh enough, the sulfuric acid rain forming in its atmosphere further underscores the danger. Even though the acid evaporates before reaching the ground, burned away by the heat, it still forms a toxic veil of clouds that wraps the planet. Looking at all of this, the answer feels inevitable. Venus's surface is utterly hostile to Earth-like life. No liquid water, no gentle temperatures, no welcoming pressure. A world like this behaves more like a natural chemical reactor, its conditions shifting toward extremes that reject every known form of life. If Mars is cold, but carries soft memories of a once wet past, Venus is a place whose surface has been locked into a state too hot, too heavy, and too acidic for life to stand a chance. Yet, as science often teaches us, when one door closes, another opens, quietly, unexpectedly. If Venus's surface resembles a kind of hell, its upper atmosphere tells a different story. At altitudes around 50 to 60 kilometers, where clouds glow in pale yellow layers, temperature and pressure settle into something surprisingly Earth-like. Temperatures there can range from 30 to 60 degrees Celsius, and the pressure is only a few times higher than Earth's, comfortably within the limits many microorganisms can endure. This has led to a bold idea. If life exists on Venus, perhaps it doesn't live on the ground at all, but in the clouds. The idea, though it sounds like science fiction, has been suggested by scientists for decades. They have wondered, could tiny microorganisms drift within those relatively gentle cloud layers, drawing energy from sunlight or from atmospheric chemical reactions? On Earth, bacteria have been found living in the air, in cloud droplets, even in mildly acidic environments. And if life can adapt that far, then imagining microorganisms floating through Venus's clouds isn't completely unreasonable. In recent years, a curious signal once stirred excitement throughout the scientific community: a possible detection of phosphine in Venus's atmosphere. On Earth, phosphine is commonly linked to biological activity. So when researchers announced they had found signs of it in Venus's clouds, many immediately wondered whether microbes might be living there. But soon after, waves of analysis, critique, and re-examination followed. Some studies found no phosphine at all. Others suggested that the signal might have been confused with other molecules. The debate continues, softly but persistently, just as sincere scientific debates always do. Even though the phosphine story has no conclusion yet, it reminds us that the search for life beyond Earth is never a straight line. Sometimes a clue seems promising, only for us to step back and double-check. Sometimes ambiguous data opens a whole field of possibilities, and it is that ambiguity, that collection of unanswered questions, that makes science so captivating. And when we step back and see the whole picture, Venus offers an important lesson. Even a planet that mirrors Earth in size, age, and general location, one we once called a sister, can become a world entirely unfit for life as we know it. This shows us that size and orbit are never the full story. Each planet is its own narrative, shaped by its climate, its geology, and its unique chemical history. And so, even though Venus may not be the first place people hope to find life, it remains a world worth questioning. Because sometimes, life doesn't appear where we expect, but in the places we least imagine. Who knows? Somewhere within those thick amber clouds, a form of life may be quietly drifting, existing in its own way, suspended within the restless skies of Earth's fiery sister. After leaving Venus behind, its restless clouds and its lingering questions about whether life might somehow drift within that acidic sky, our journey continues, drifting farther away from the familiar rocky worlds. The space between planets stretches open, and ahead lies a region where the giant planets reign, radiating their gravitational strength like ancient pillars holding the rhythm of the entire solar system. And among them rises one world more striking than all the rest, a massive, banded, swirling, and mysterious globe of gas. That world is Jupiter. Jupiter appears like a colossal lantern painted with bands of brown, gold, cream, and red, each one swirling in winds far stronger than any storm on Earth. These cloud bands are never still. They shift constantly, creating a canvas that changes moment by moment. Across this hazy surface, the Great Red Spot, a centuries-old storm, rotates like a massive, unblinking eye, large enough to swallow Earth several times over. Looking at Jupiter, one does not see a peaceful world. One sees a place forever in motion, powerful and brimming with energy. Looking deeper into Jupiter's structure, we discover that this planet has no solid surface like Earth's. There is nowhere to stand, no ground to set foot upon. The farther one descends, the more the pressure climbs, rising to levels that crush all familiar forms of matter. Hydrogen gas in the upper layers is slowly compressed into liquid, and deeper still, it transforms into metallic hydrogen, a strange state that exists only under unimaginable pressure. In such an environment, it's hard to imagine any Earth-like life taking hold. While there have been dreamy speculations about floating organisms drifting through Jupiter's clouds, delicate balloon-like beings feeding on light and atmospheric chemistry, these ideas remain imaginative possibilities rather than evidence-based conclusions. But the most compelling part of Jupiter is not the planet itself. It is the vast family of moons that orbit around it. If Jupiter is a giant, gaseous father, then its moons are its many children, each with its own personality and its own story. Among the more than 70 known moons, some are rocky, some tiny, some wrapped in ice, and some harbor deep, dark oceans beneath their frozen shells, places where microbial life might have found a way to survive. Europa is one such world, a bright, smooth sphere of ice, beautiful like a cold gem. Its surface is etched with countless long fractures, like cracks on a sheet of ice pushed from within. Scientists believe that beneath its tens of kilometers of ice lies a global ocean of liquid water, kept warm by tidal forces from Jupiter's immense gravity. If there is any place in the solar system capable of hosting extraterrestrial life, Europa is always among the first to be considered. Nearby is Ganymede, the largest moon in the entire solar system, even bigger than Mercury. Its surface blends bright regions scarred by icy erosion with darker, older terrains. But what makes Ganymede truly special is the evidence suggesting that beneath its thick, icy shell lie multiple layers of oceans, each separated by rigid layers of ice. This structure makes Ganymede resemble a many-layered cake, with each layer offering its own environment. If Europa is fascinating for its single vast ocean, then Ganymede is captivating because it may hold several oceans stacked one atop another. And then there is Callisto, a world scarred with craters, older than even the oldest regions on Earth. Callisto appears quiet, as though frozen in time. Yet beneath its pitted surface, scientific models suggest a subsurface ocean may exist, not as active as Europa's or Ganymede's, but still potentially capable of hosting the chemical conditions necessary for microbial life. That quietness is what makes Callisto interesting. Life does not always need a dynamic world. Sometimes a calm, stable place can nurture simple forms of life. Looking at all these moons, one can see that Jupiter serves as a hub of hidden possibilities. While the giant planet itself is unlikely to support life, its icy children open up a breathtaking landscape of questions. Beneath their frozen crusts may lie oceans larger than any on Earth. In the absolute darkness at the ocean floors, chemical reactions may have been unfolding for billions of years, requiring no sunlight, only tidal heat and minerals from the seafloor. And if that is true, life could be existing right now in complete darkness, unaware that above its icy roof stretches an entire universe. That thought brings forth a gentle, evocative image. If Jupiter is a giant gaseous father, then its moons are the children keeping secrets. And those secrets may hold the answer to one of humanity's oldest questions. Are we alone in the universe? And so, even though the journey from the rocky worlds to a massive gas giant may feel like stepping into a different chapter, everything still flows into a single stream. The search for life, the search for signs, the search for the faintest clues across the vastness of space. Because somewhere among those icy moons quietly circling Jupiter, one or several of them may be holding the answer humanity has awaited for centuries. After taking in the vast family of Jupiter, where each moon carries its own personality and its own quiet promise, one name naturally pulls the attention of anyone searching for life beyond Earth. Among the icy worlds circling the giant planet, there is one moon that science keeps returning to, keeps questioning, keeps watching for even the faintest sign. That moon is Europa, a world that looks cold and silent, yet hides an ocean that may be deeper than any ocean humanity has ever known. Seen from afar, Europa appears as a bright, smooth sphere, as if sculpted from pure ice. Its surface doesn't resemble crater-filled moons or rugged dark terrains. Instead, Europa carries a gentle smoothness, traced by countless long, winding fractures, lines that curve across its shell like frozen veins on a cold, pale globe. These cracks carry soft, reddish-brown hues, as if some mysterious chemical has brushed color onto the ice. Viewed more closely, the image becomes even more enigmatic. A frozen orb streaked with long, branching lines, as though its outer shell is slowly shifting over time. Those fractures are the first clues that Europa is not a solid block of ice. They form as its icy crust stretches and compresses under the immense tidal forces from Jupiter. Forces so powerful they can bend and tug a shell tens of kilometers thick. Beneath that shell, scientists believe a global ocean of liquid water spreads across the entire moon, possibly tens or even hundreds of kilometers deep. An ocean so vast that its total volume may exceed the combined water of all Earth's oceans. The strange thing is that Europa lies far farther from the sun than Earth does, and the faint sunlight at that distance cannot possibly keep water in liquid form. And yet, the water does not freeze solid. The secret lies in the gravitational interplay between Europa, Jupiter, and nearby moons. As Europa orbits Jupiter, the giant's powerful gravity stretches and squeezes the moon over and over, generating heat deep inside its core. This phenomenon, known as tidal heating, is the energy source that prevents Europa's ocean from freezing, making it one of the most promising locations for extraterrestrial life in the solar system. To understand why liquid water beneath ice matters so much, scientists often compare Europa to certain extreme environments on Earth. At the bottom of Earth's deepest oceans, where sunlight never reaches, where temperatures hover near freezing, and where crushing pressures dominate, hydrothermal vents have been found. From these vents, life flourishes. Bacteria that live on chemical energy, eyeless tube worms, bizarre organisms with remarkable adaptations. All of them exist completely independent of sunlight, relying instead on the reactions between heated water and the rocky seafloor. Looking at Europa, scientists begin to wonder, if Earth can sustain an ecosystem like that in absolute darkness, could Europa, with an ocean warmed by tidal energy, harbor similar environments? And if so, could hydrothermal vents on Europa's ocean floor nurture extraterrestrial microorganisms for billions of years? This possibility is not just reasonable, it has become one of the strongest hypotheses in the search for life beyond Earth. Beyond its cracks and surface structures, Europa sends other signals into space. Spacecraft that once flew past Europa detected hints of water plumes erupting through its fractures, jets of vapor, ice, and tiny molecules shooting into space before falling back onto the surface. These plumes are like faint breaths rising from the hidden ocean, as if Europa were quietly coughing, revealing secrets it has held for billions of years. When scientists analyzed the composition of these plumes, they found traces of salts and molecules possibly tied to geochemical activity. This strengthens the idea of an active interaction between water and rock on Europa's seafloor. Thinking about this, it becomes easy to imagine a peaceful yet profound scene. Beneath a thick shell of ice in eternal darkness, there may exist an ocean warmer than expected, with slow-moving currents, ongoing chemical reactions, and tiny organisms, if they exist, living quiet, unknowing lives. They might not realize that millions of miles away, a civilization is trying to find them. Life there, if present, might be simple, perhaps only ancient forms of bacteria, but their existence would prove that the universe has not produced life only once. Europa, with all these possibilities, stands among the brightest candidates in the search for extraterrestrial life. Not because it is beautiful, not because it is nearby, but because it holds the fundamental ingredients science considers essential: liquid water, tidal energy, and the interaction between rock and water. These are the three elements that could build the foundation of an ecosystem. And in the end, when looking back at everything we know, Europa feels like an ocean hidden beneath a sheet of ice, deep, mysterious, and perhaps quietly stable for billions of years. A world without sunlight, without a sky, but possibly with life. Europa may not be a place where humans can stroll across solid ground, but it may be a place where extraterrestrial life is waiting to be found, drifting softly in the darkness of the ocean beneath its cold, frozen shell. When speaking of Europa and the ocean stirring beneath its frozen shell, it feels natural for the mind to drift toward its close neighbors, Jupiter's other moons, where darkness may also hide deep oceans no less mysterious. If Europa is the shining star among worlds that might hold liquid water, then Ganymede and Callisto are the next chapters, expanding the idea that throughout the solar system, water may exist quietly in places that seem cold and motionless. Ganymede, first of all, is a world that leaves anyone who sees its images in quiet awe. It is the largest moon in the entire solar system, so large, in fact, that it surpasses Mercury in size. Gazing at Ganymede's surface, one sees a patchwork of smoother, brighter regions and darker, ancient, cratered plains. The bright areas appear to be younger zones, where the ice was renewed by some form of tectonic activity long ago. The darker regions preserve a long record of cosmic impacts. Together, they make the surface of Ganymede feel like a handwritten manuscript, many passages written at different moments, each with its own tone, yet all blending into a long, intricate geological story. What makes Ganymede even more extraordinary is that it possesses its own magnetic field, something no other moon in the solar system has. This magnetic field suggests movement of electrically conductive material inside, a process that may involve a metallic core or interactions between liquid and solid layers. When scientists analyzed data from the Galileo spacecraft, they found that Ganymede's interior is far from simple. Instead of a single ocean, Ganymede may hold multiple underground seas, stacked between thick layers of ice, like an enormous layered cake where water and ice alternate again and again. This opens up a fascinating possibility. Each ocean layer could offer its own environment, each with its own chemistry, perhaps suitable for different types of microbial life. Yet, because Ganymede is so large and its structure so complex, understanding it becomes more challenging. Do these oceans touch a rocky seafloor? This is an essential question, because interactions between water and rock can create chemical energy, the kind needed to support life. Some models suggest that the deepest layer of water may indeed reach solid rock, creating reactions similar to those at Earth's deep-sea hydrothermal vents, where entire ecosystems thrive. Other models suggest that Ganymede's total depth and layers of ice could insulate the oceans, preventing any contact with rock. Either way, the mystery remains, and that mystery is what makes Ganymede so compelling. A vast, cold, beautiful sphere that may hold multiple silent oceans within. Leaving Ganymede behind, we arrive at Callisto, a moon that seems to stand outside the grand motions of its siblings. While Europa is etched with cracks and Ganymede shows signs of tectonic renewal, Callisto feels like an ancient world left untouched by time. Its surface is covered in impact craters billions of years old, and because no strong geological processes have refreshed its crust, those scars remain across its entire history. Looking at Callisto is like looking at a painting from the dawn of the solar system, one that has never been revised. Its stillness makes it appear peaceful, yet also profoundly solitary. But beneath that aged exterior, Callisto may hide an unexpected secret. Although it does not experience strong tidal forces like Europa or Ganymede, many structural models suggest that a layer of liquid water may exist between its ice layers. Not an ocean as vast as Europa's, but still deep and stable enough to create a chemically rich environment. The mixing between cold surface ice and the warmer rocky interior could produce important chemical reactions. And while Europa and Ganymede may host vigorous interactions between rock and water, on Callisto these processes might unfold more softly, more slowly, yet still potentially capable of supporting life. Both Ganymede and Callisto are dark, cold worlds, far from the warmth of the sun. Their surfaces offer little hope, thin or non-existent atmospheres, temperatures so low that water freezes instantly, and no sunlight strong enough to warm them. But life, if it exists, does not always need light. It needs liquid water, energy, and the right molecules. And all three ingredients may very well exist beneath the icy shells of Ganymede and Callisto. The strange thing is this: the more we learn about these worlds, the more we realize that the most lifeless-looking places may be the most alive beneath the surface. The outer crust may be dry, still, cratered, and frozen, but tens of kilometers below could lie vast oceans where chemical reactions continue, where water and rock touch in the darkness, where energy is quietly generated. When Europa, Ganymede, and Callisto are placed together in a single picture, a gentle yet powerful idea emerges. In the solar system, worlds with liquid water are not limited to Earth or ancient Mars. They exist subtly in the shadows of the giant planets' moons. They hide beneath cold ice, not boasting, not moving loudly, yet holding all the essential conditions for life. And so, Ganymede and Callisto become indispensable parts of this search. They remind us that sometimes life may choose to live in darkness, in silence, and in oceans no one can see. These water-rich worlds exist quietly, like hidden gems in the treasury of the cosmos, waiting for the light of science to reach them one day, revealing stories humanity has only just begun to imagine. After passing through the shadows of Ganymede and Callisto, where hidden oceans might be quietly curling beneath thick layers of ice, our journey carries us farther still, crossing the vast distance between the giant planets to reach a world that feels like a piece of cosmic artwork at first glance. This is Saturn, the planet adorned with the most magnificent ring of ice and stone in the entire solar system. A world both dreamy and immense, filled with mysteries that science cannot look away from. Saturn appears as a colossal sphere of gas, gentle yet powerful, encircled by rings so broad they stretch hundreds of thousands of kilometers from the planet's center. These rings are not a solid structure, but countless particles of ice, rock, and dust, ranging from grains no bigger than sand to chunks the size of boulders. When sunlight catches them, they gleam as a shimmering band of crystals, like a massive halo carved from frozen light. Their beauty makes Saturn feel not just like a planet, but a symbol of elegance drifting in the darkness of space. Despite its delicate appearance, Saturn is not a place suited for Earth-like life. It has no solid surface, no place to stand, no hospitable atmosphere. Like Jupiter, it is an immense ocean of gas, where pressures and winds exceed anything humans have ever experienced. Yet, also like Jupiter, the most intriguing parts of Saturn are not found within the planet itself, but in its rich and varied family of moons. If Jupiter is a mighty king surrounded by powerful offspring, Saturn is like a vast home full of rooms, each moon a separate chamber with a different story. Among more than 80 known moons, two names shine brightest in the search for life: Enceladus and Titan. Each world offers a different window into possibility, forming a long, compelling chapter in the story of the solar system's most promising places to look for life. Enceladus, the first of these moons we visit, is so small it could fit comfortably inside a country on Earth. Yet its modest size hides a profound secret. Seen from afar, Enceladus is almost completely white, brilliant under the sun like a perfect snow globe. Its icy surface reflects so much light that it is one of the brightest objects in the solar system. Despite its smallness, Enceladus possesses a remarkable ability. It ejects water into space through fractures near its south pole. These plumes, observed many times, are not only beautiful, but contain evidence that beneath the ice lies a vast, salty ocean. Titan, on the other hand, is an entirely different world. If Enceladus is the white glow of snow, Titan is the soft, amber haze of fog. Titan is Saturn's largest moon, and the only moon in the solar system with an atmosphere thicker than Earth's. Not only thick, but filled with methane and organic molecules, forming a golden mist that blankets its entire surface. Beneath that haze lie rivers, lakes, and even seas, not of water, but of liquid methane. The imagery feels like a prehistoric Earth, where organic chemistry runs wild and constant. Looking at Enceladus and Titan, one can sense that each moon is like a separate room in Saturn's expansive home. Enceladus is the cold, icy room where liquid water flows in the darkness of an underground sea. Titan is the amber room, where organic chemistry unfolds like a natural laboratory, offering a completely different path life might take. Each room tells its own story, and within each story lies something uniquely compelling to science. Saturn, with its glittering rings and diverse moons, resembles a nursery for strange worlds. Not every world holds water, and not every world mirrors Earth's conditions. But it is precisely this diversity that opens the possibility that life, if it exists in the solar system, may be experimenting with many different modes of survival. Perhaps life hides beneath Enceladus's icy crust, fed by hydrothermal reactions. Perhaps life floats in Titan's frigid methane lakes, following chemical rules entirely different from those on Earth. Each hypothesis opens a new branch of the story, and each branch makes the journey more thrilling. And when we view Saturn as a house of many rooms, each moon its own world, we begin to understand that to find life, we must open each door one by one. We cannot know what waits behind any given door. But that uncertainty is the most beautiful part of exploration. Every world might be a chapter in the universe's vast book, and every chapter may contain a passage science has never read before. For this reason, when we leave the hidden oceans of Ganymede and Callisto to arrive at Saturn, we are not abandoning the idea of liquid water or conditions suitable for life. We are simply entering a new home, where the next door waits to be opened. And the next part of the story will lead us into the brightest icy chamber of Saturn, where Enceladus gently releases its plumes into space, like a quiet invitation to explore the ocean hidden beneath its frozen shell. Standing before the first door in Saturn's great celestial home, where each moon feels like a room with its own story, it feels only natural to open the one that stirs the most curiosity: the door of Enceladus. This is the room science returns to again and again, not because of its size or grandeur, but because of the subtle, powerful signals rising from its icy surface. If Saturn is a vast house, then Enceladus is its brightest room, where the reflected light is so striking it's hard to look away. Enceladus is a small moon, So small, it's hard to believe it could hide something as immense as a global ocean inside it. But its modest size is part of what makes it so uniquely beautiful. Its surface is coated in a smooth, brilliant layer of ice, reflecting sunlight so intensely that it looks like a giant snow pearl floating through the dark. Unlike Callisto with its rugged shadows or Europa with its intricate fractures, Enceladus is simpler, purer, like fresh snow that time has never had the chance to wear down. But Enceladus is far more than a lovely frozen sphere. Beneath its quiet exterior lies one of the most astonishing discoveries in the history of exploring the solar system. When the Cassini spacecraft flew past Enceladus's south pole, it detected jets of vapor, ice particles, and tiny crystals erupting from cracks in the surface. These plumes stretched hundreds of kilometers into space, rising like delicate, pale fountains against the void. The sight was both beautiful and startling. A tiny, frigid moon releasing constant geysers of water into space, almost as if whispering secrets from the ocean hidden below. These plumes weren't just stunning to look at. They were powerful enough that some of their material drifted outward to help form Saturn's faint E-ring. No one had predicted that a single moon could feed an entire planetary ring before Cassini made its discoveries. When Cassini flew directly through those plumes, it performed detailed analyses. What it found captured the attention of scientists everywhere. The icy grains and vapor contained liquid water that had been pushed upward and frozen, salts, and even organic molecules. The presence of salt suggested that the water beneath the ice is likely a salty ocean, much like Earth's own oceans. And the presence of organic molecules hinted that the building blocks needed for life, at least microbial life, might exist or might once have existed there. This transformed Enceladus into one of the most promising places in the entire solar system when it comes to the possibility of life. Not because it resembles Earth, but because the environment beneath its icy shell mirrors the kinds of settings where life has thrived on Earth without sunlight. On the ocean floor of Earth, hydrothermal vents have pumped mineral-rich hot water for billions of years. Around those vents, life has flourished, from simple bacteria to strange, eyeless creatures, all surviving on chemical energy, produced by reactions between water and rock. Remarkably, data from Enceladus suggests that similar hydrothermal vents might exist on the floor of its hidden ocean. When Cassini analyzed the plume particles and gases, it found signs of nanosilica, a substance that forms when hot, mineral-rich water meets rock. This sparked the hypothesis that beneath Enceladus's icy shell, water is interacting with a rocky core, producing powerful chemical reactions, just like those found at the bottom of Earth's oceans. If this is true, then Enceladus has water, liquid water, salt, organic molecules, and chemical energy. The four most important ingredients for creating and sustaining life. In a tiny frozen world locked in eternal darkness, there may exist a vast ocean beneath the ice, holding the very conditions in which simple life could have learned to endure. Thinking of Enceladus, it's easy to picture a peaceful, deep ocean, its surface sealed by thick ice, but beneath it, quiet currents flowing around vents on the seafloor. In that darkness, if life exists, it would live softly, without sunlight, relying only on steady chemical energy. Such an ecosystem could persist for billions of years without drastic change. It is this balance of simplicity and complexity that makes Enceladus one of the most compelling candidates in the search for life. Not because it has a beautiful surface or impressive scale, but because it holds a sealed, warm, chemically rich ocean, a nearly perfect cradle for humble microbial forms. The plumes that rise into space feel like gentle whispers, as if this small world is inviting us to come closer and listen to the story hidden within. And watching Enceladus drift quietly around Saturn, with its southern geysers rising like breath into the cold void, one slow thought emerges. Sometimes the most hopeful places are not giant planets, not bright worlds filled with light, but tiny frozen moons where oceans lie hidden and life, if it exists, survives in ways we have never imagined. Enceladus is a reminder that the universe is full of soft surprises and that its greatest secrets may come from its smallest worlds. After leaving behind the bright, icy world of Enceladus, where plumes rise like the whispers of a hidden ocean, our journey naturally turns toward another of Saturn's moons, a place that feels both familiar and foreign at first glance, as though we are gazing at an alternate Earth veiled in thick mist. This is Titan, Saturn's largest moon and one of the most intriguing worlds in the solar system when it comes to the possibility of life emerging in ways science has yet to fully grasp. If Enceladus is the glowing ice chamber in Saturn's great house, then Titan is the room lit with a dim amber glow, where everything is coated in a soft, orange haze. Titan is wrapped in an exceptionally thick atmosphere, thicker than Earth's, made primarily of nitrogen, with methane and other simple molecules mixed in. The methane and hydrocarbon compounds suspended in the air create Titan's orange fog, bathing the world in a light that feels like an eternal, muted sunset. Peering through that haze, using radar and data from the Cassini spacecraft, scientists uncovered something extraordinary. Titan is one of the few places beyond Earth that has flowing liquids on its surface. Titan has rivers, lakes, and even seas. But these rivers do not run with water. They are carved by liquid methane and ethane. The Great Lakes near Titan's North Pole are not made of water, but of cold hydrocarbons, like eerily beautiful alien seas where waves are shaped not by ocean breezes, but by faint shifts within a methane-rich atmosphere. Temperatures on Titan drop to around 150 degrees, cold enough to turn water into rock as solid as granite. In such conditions, methane becomes a liquid, taking on the role water plays on Earth. Titan's allure lies not in its resemblance to our planet, but in the way it mirrors Earth by inverting every familiar rule. If water is the medium for life on Earth, then perhaps on Titan, liquid methane could serve as the foundation for an entirely new kind of biology. Within Titan's thick atmosphere, sunlight sparks countless chemical reactions, creating complex organic molecules. These compounds drift downward like gentle snow, settling onto the surface and forming what some scientists call organic sludge, a soft layer rich in carbon-based material, the building blocks of life's chemistry. But on Titan, these compounds exist in a world too cold for liquid water. Their presence transforms the moon into a vast natural laboratory where organic reactions may be unfolding over millions of years, potentially self-organizing, potentially evolving along paths never seen on Earth. From this emerges a quiet, lingering question. What if life does not need water at all? What if somewhere in the universe, life chooses methane as its solvent? On Earth, life nearly always depends on water, but Earth is only one example among countless possible chemistries. Titan encourages us to imagine that simple organisms might exist in its liquid methane lakes, fueled by reactions entirely different from the ones familiar to life on Earth. The idea may sound far-fetched, but it is not fantasy. Some scientists have simulated chemical reactions in liquid methane and found that molecules can indeed self-organize, forming membranes or stable structures under certain Titan-like conditions. Earth-like life cannot exist here. There is no liquid water, and the cold is overwhelming. But a different kind of life, adapted to hydrocarbon seas, could be hiding beneath Titan's orange haze. To understand Titan more deeply, humanity sent the Huygens probe, part of the Cassini-Huygens mission, which landed on Titan's surface in 2005. When it touched down, it recorded a landscape that looked like the bed of an ancient stream, as though a river had once flowed and frozen long ago. Data suggested that Titan may experience a methane-based weather cycle similar to Earth's water cycle. Methane clouds forming, methane rain falling, streams carving through the landscape, then evaporating back into the atmosphere to begin the cycle again. A planet with methane weather, strange yet familiar, like a dream of a world written entirely in the language of hydrocarbons. And Titan's story is far from over. In the coming years, NASA plans to send a mission called Dragonfly, a large 8-rotor drone designed to fly like a robotic dragonfly through Titan's sky. It will land in multiple locations, study organic chemistry, and investigate whether life could exist there. The idea of a robotic dragonfly drifting through Titan's amber atmosphere, quietly listening for secrets hidden beneath the haze, paints an image both peaceful and full of hope. Dragonfly will explore not just the surface, but places we have only imagined. Organic slush fields, methane lake shores, and perhaps the chemical traces of pre-biological reactions. When we place Titan alongside Enceladus, we see two worlds that offer different but powerful possibilities for life. Enceladus asks whether life can arise at the bottom of a dark, heated ocean. Titan asks whether life can begin in freezing methane, guided by complex organic chemistry. One world shaped by water, one shaped by hydrocarbons. Together, they open doors to possibilities far beyond what humanity has known. And so, moving from Enceladus to Titan does not feel like leaving a promising world for a lesser one. Instead, it feels like stepping into the next chapter of the universe's great book, where each page reminds us that life, if it exists beyond Earth, may be experimenting with paths we have barely imagined. Titan drifts quietly around Saturn, like a world the cosmos crafted to whisper to those willing to listen. Within the orange haze, within the methane lakes, within the organic sands, the oldest secrets of life in the solar system may be waiting. After leaving Titan behind, with its mirror-still methane lakes and its eternal orange haze, the journey drifts even farther out into the solar system, into regions where sunlight fades until it becomes nothing more than a faint, trembling dot in a cold, dark sky. And at these distant edges, where everything grows quieter, slower, and colder, a group of worlds appears. Places humanity has only brushed against once, and only for a fleeting moment. These worlds feel like enormous locked doors, standing before us and inviting imagination to wander freely. They are Uranus, Neptune, and especially Triton, the moon of Neptune. Uranus and Neptune are known as the ice giants, yet despite the name, they are not frozen spheres in the way one might picture. Instead, they are massive globes filled with deep layers of gas and ices, wrapped in thick, frigid clouds. Uranus carries a soft turquoise hue, drifting around the sun while tilted dramatically on its side, as though knocked over by a tremendous ancient impact. Neptune, darker and deeper in color, glows with the cold beauty of a gemstone suspended in shadow. Both are unique, but neither is expected to host Earth-like life. There is no solid surface. The internal pressure is overwhelming, and the temperatures are so low that familiar biology seems impossible from the start. But just as with Jupiter and Saturn, The most captivating stories do not belong to the planets themselves, but to the moons that circle them. And among those distant satellites, Triton, Neptune's largest moon, stands out as a source of wonder and confusion. Triton is not merely a frozen moon, it may be a world that originated elsewhere. It orbits Neptune in the opposite direction of the planet's rotation, a clue that it may have been captured from the Kuiper Belt. This makes Triton not simply a moon of Neptune, but a bridge to the far-off icy realms beyond the solar system's edge. Triton's surface is coated primarily in nitrogen ice, forming a landscape unlike anywhere else. But what makes Triton truly fascinating is what Voyager 2, the only spacecraft ever to visit this region, discovered during its brief flyby. On Triton's surface, it found signs of activity, geysers erupting nitrogen ice and dust into the sky, sending pale columns upward for kilometers before weak winds blew them into long streaks across the surface. These icy plumes are astonishing. In a world so cold that nitrogen freezes solid, something energetic is happening beneath the surface, as though a quiet warmth is trapped within the moon's icy shell. As Voyager 2 gathered data, scientists began to suspect that beneath Triton's nitrogen crust might lie a subsurface ocean, not necessarily pure water, but perhaps a mixture of water and ammonia, acting as a natural antifreeze. Such a mixture could remain liquid even under extreme cold. And if such an ocean truly exists beneath Triton, it could resemble the hidden environments suggested for Europa or Enceladus, a dark, sealed chamber rich with chemical reactions. The possibility of this ocean, though unconfirmed, is enough for Triton to join the list of worlds that may hold microbial life somewhere within our solar system. Yet what makes Uranus, Neptune, and Triton remarkable is not only the possibility of liquid water, it is the unfamiliarity, the profound mystery surrounding them. We know so little about these worlds that nearly everything we understand today comes from a single flyby of Voyager 2 in the late 1980s. Since then, no spacecraft has returned. Every image we have of Triton, Uranus, or Neptune comes from those few hours, like a single glance through a barely opened door before it quietly swung shut again, leaving behind countless questions. People still wonder what hides beneath Neptune's sapphire clouds, or deep within Uranus's icy interior. How many of their moons hold hidden oceans? Was an object like Triton once part of a larger world on the solar system's distant frontier? And do Triton's icy geysers work the same way as Enceladus's? There are no clear answers, and that absence is what makes these places feel like unwritten chapters, untouched pages in the great story of the solar system. Looking toward these far-off worlds feels like gazing into a region of the cosmos wrapped in shadow, where time seems slower and sunlight is little more than a fragile breath. Yet this region is also a place of hope. Hope that within the cold silence, secret oceans are still flowing quietly. Hope that these worlds carry stories of life that humanity has never heard. Each distant, icy body is a folded page, and each page may hold a crucial line in the story of our search for life. And as the journey leaves Titan behind and moves into these darker regions, it does not feel like leaving mystery for something less interesting. Instead, it is like expanding the map of curiosity itself, discovering that even where the sun is only a dim pinprick in the sky, the universe continues to form waters, ice layers, and quiet movements beneath frozen crusts. Perhaps one day, when new spacecraft return to Neptune or Uranus, these distant worlds will share the secrets that, for now, we can only imagine. Somewhere in that darkness, there may be an ocean flowing in perfect silence, waiting to be seen, waiting to be understood, waiting to take its place in the larger story of our most timeless question. Could life exist elsewhere in the solar system, beyond Earth? After drifting past those distant worlds where sunlight fades into nothing more than a faint, trembling point, and after quietly observing the mysterious stillness of Uranus, Neptune, and Triton, it feels natural to look back and take in the entire journey from a higher vantage. Like standing on a peaceful hill at the end of the day and gazing down at the road already traveled, we slowly realize that the solar system is not just a collection of planets. It is a map of clues, questions, and soft whispers from different worlds about the possibility of life. And in that moment, it feels right to redraw this map in the gentlest way. Not as a dry list, but as a tapestry woven from images and emotions. If we begin with what is closest, then Mars must come first. The red planet has become the symbol of the question, has life ever existed beyond Earth? Not because Mars today is a hospitable world, but because the traces left on its surface tell a story very different from its present dryness. Long valleys shaped like ancient riverbeds, layers of sediments hinting at lakes, minerals that form only in water. All of these whisper that Mars was once warmer, wetter. And if any place in the solar system once resembled early Earth, it would be ancient Mars. Its geology remains an open book, and every rover gently turning its wheels is flipping through its pages, searching for clues to a question humanity has carried for centuries. With the evidence we have, Mars stands as the strongest candidate for having once hosted life, even if we still cannot say whether that life might linger in sheltered pockets deep underground. Moving away from Mars, the map leads us to colder, farther realms where air holds no oxygen, where sunlight is weak, but where liquid water might exist in hidden darkness. The first among them is Europa, Jupiter's icy moon. Europa captures scientific attention because of its thick frozen shell and the global ocean beneath it. The cracks on its surface look like veins on a slowly shifting body, while tidal forces from Jupiter keep its hidden ocean liquid and restless. That ocean may be many times deeper than Earth's, and where water meets rock at the ocean floor, chemical energy could feed microbial life. Water plumes rising from Europa, observed more than once, suggest that the ocean below is not silent. For that reason, Europa sits at the top of the list of places that might harbor life right now. Enceladus, Saturn's tiny moon, stands beside Europa in that list, but for its own reasons. The plumes erupting from Enceladus's south pole feel like confessions from the ocean below. When Cassini flew through those plumes, it detected water, salt, and organic molecules, the three most essential ingredients of life. Many clues suggest that hydrothermal vents may exist on its ocean floor. Enceladus's small size does nothing to diminish its potential. If anything, its simplicity makes it an incredibly compelling suspect, a world where life, if it exists, may have evolved quietly for billions of years without sunlight. Alongside Europa and Enceladus are Ganymede and Callisto, two other moons of Jupiter. Ganymede has its own magnetic field, and internal models suggest layers of oceans separated by sheets of ice. Callisto is older, quieter, but may still hold a deep layer of liquid water. These worlds lack the strong energy signatures of Europa or the dramatic plumes of Enceladus, but their possible hidden oceans earn them a place on the map. They are water worlds in the dark, places science hasn't studied long enough to fully understand. Titan, Saturn's largest moon, opens a completely different branch of possibility. A world of liquid methane, of thick orange atmosphere, of methane weather patterns that mirror Earth in reverse. Titan has no liquid water on its surface, but it holds so much organic chemistry that it feels like a natural laboratory, constantly sculpting carbon-based molecules. Complex organics fall like snow, methane rivers flow into methane lakes, and the landscape feels like an eerie dream of a world where everything is written in the language of hydrocarbons. If life could arise from methane instead of water, Titan could be its cradle, a place for biology unlike anything on Earth. No one knows if that is possible, but Titan's strangeness gives it a magnetic pull in the search for life. Even Venus, despite its surface being a hellish furnace, has been mentioned before in this conversation. Not its surface, but its cloud layers, where pressure and temperature are gentler, and where controversial chemical hints once sparked debates. The possibility is slim, but even the faintest possibility keeps Venus from being erased from the map entirely. And when we look at the full map of suspicious, promising, mysterious places, a quiet insight emerges. Some worlds may have once been habitable, like ancient Mars. Some may be habitable today, like Europa or Enceladus. Some might nurture entirely alien forms of life, like Titan, and some whisper only faint questions, like Venus's clouds. All of this leads to a soft truth. Humanity has not yet found life beyond Earth, but the absence of an answer has never made the journey any less meaningful. Each year brings new spacecraft, new telescopes, new windows into the dark, new puzzle pieces falling onto a table where the final picture remains unknown. When we view the solar system with the eyes of someone who has wandered through its worlds, it does not feel like a static image. It feels like holding a mysterious storybook, where each page is a world, each world an unfinished chapter, and each chapter invites us to read on. From dry red Mars to white icy Europa, to softly glowing Titan, to blue-gray Triton, all are connected by one quiet, powerful question. Are we alone in the solar system? And in the stillness of night, as that map glows gently in the mind, the question becomes an invitation, an open door to turn the page and continue the journey. As the map of the solar system's most promising worlds slowly brightens, stretching from Mars to the dark hidden oceans, from Titan's amber haze to Triton's frozen quiet, the journey gently reaches its final chapter. And in this moment, while the mind still holds the majestic images of distant worlds, a soft calm arrives, as if the universe itself is quietly inviting us to return, to close the door on this voyage, and to settle once more on Earth, where everything familiar is waiting. Returning does not mean leaving those stories behind. Returning simply means guiding the mind back to its starting place, a quiet room, a waiting pillow, a breath growing steady and sinking with the silence of the night. And in that familiar space, we carry the scenes we've traveled through like lanterns floating across the ceiling of memory, glowing softly each time we close our eyes. This journey, though spanning so many worlds, began with one very small question. Could life exist somewhere beyond Earth? That question led us to Mars, where ancient valleys look as though rivers once flowed, where sediment layers echo the voice of a wetter age. Together, we revisited giant volcanoes, deep chasms, and layers of rock gently turned over by patient rovers, storytellers made of metal and dust. We wandered across dunes, over stones, as if our own eyes leaned down to examine secrets Mars has kept for billions of years. Leaving Mars, we drifted toward the icy moons of Jupiter and Saturn. Europa appeared with its long cracks like the frozen veins of a world slowly shifting beneath its shell. Enceladus exhaled pale plumes into space, carrying the chemical breath of the salty sea beneath. Ganymede and Callisto lingered farther out, darker, quieter, yet still holding layered waters we can only imagine. Titan glowed like an amber dream, where methane streams flow like liquid glass between frigid shores. Each world opened a different corner of the story of life, some whispering about water, others about energy, others about organic chemistry, and some asking whether life might choose a path entirely unlike anything we know. Then the journey carried us farther still, to worlds where the sun is only a dim point, where time drifts like the slow breathing of a sleeping universe. Triton, Neptune, and Uranus felt like the uncolored regions of the map, dark rooms we only glimpsed for a moment as Voyager 2 slipped by. And because our knowledge is so limited, these worlds have become places of imagination, places where we lay questions about unseen oceans, unmeasured chemical reactions, and secrets still waiting for names. When we look back at the entire voyage, a gentle thought rises. Perhaps we have not yet found them, the neighbors humanity has dreamed of for so long. But the search has shown us our own home more clearly, the blue world spinning slowly through the vastness. We understand water better, energy better, habitability better, and why Earth is such a rare and precious refuge. The question of life beyond Earth, in a way, reflects back onto the life all around us. Our rivers, our mountains, our oceans, our soil holding the stories of this planet. And woven through everything we've learned is this quiet truth. We seek not to fill a void, but to feel more deeply connected to the universe. Just knowing that other worlds once had water or energy or chemistry capable of supporting life makes the night feel less lonely. The feeling is like looking up at a star-filled sky, not to find any specific star, but simply to know we are standing in a vast universe where possibilities shine like distant lights. Now, as the journey closes, we return to our room, where the light has been dimmed, where the pillow waits, where the breath slows just a little. And in that space, we can let the mind float gently, like a small ship drifting across a night ocean. If we close our eyes, we might imagine ourselves gliding past worlds that glow like lanterns against the dark, before quietly placing a final question at the edge of sleep. Tomorrow, what new whisper will Mars reveal? Will a simple stone or a delicate trace of chemical salt hint at something more? And beneath Europa's ice, could something, however small, be waiting to be known? These questions are not here to keep us awake, but to open sleep like a soft door, letting possibilities continue to drift in our dreaming mind. And so, as the images of the journey sink gently into the dark, like lanterns dimming one by one, we offer a quiet wish. May sleep arrive softly, light as wind drifting between planets. And who knows, perhaps tonight, in a dream, you'll be the first to glimpse life on another world. Perhaps the universe will share a small story it cannot tell in daylight. And when morning comes, you may wake with the quiet sense that even if we have not found them yet, we have touched a vast part of the universe, and the universe has brushed gently back.